Hello everyone, welcome back to my channel. My name is Bin Yan. I'm a material scientist working on the field of computational material science and autonomous synthesis. This is my channel for sharing my understanding of material science. I will post either my comments on some up-to-date papers, some mini tutorials of material science, as well as some funny things as a material scientist. Please subscribe if you want to get up-to-date information from me. Today, I'd like to show you with some of my understanding about predictive synthesis of ceramic materials. It's a broad topic, as you see, since we are talking about how to make a ceramic materials, and ceramic are probably the most versatile materials in the world. So let's get started. All the details about some synthesis examples in these videos can be found in these 4 papers. The first paper is the paper I get involved when I work as a postdoc in CETA group, while the last 3 papers are actually what I did dating back to my PhD at McGill University in Canada. Okay, let's come back to the story. So we all know that we can do computational material science to accelerate the discovery of materials, right? So the way we do it to use some modeling tools such as density functional series. Like dating back to 1990s, the first paper in Science about computational material science is actually from my current advisor, Professor Gerber Cedar. And at that time, he actually proposed, we can predict a variety of properties such as the voltage of intercalating electrode materials for lithium-ion batteries by doing DFT calculations. And now it has already been like more than 30 years, right? So currently, we are not just calculating properties of single materials, because the data we can accumulate or the calculation we can scale up has already reached to the next level. Now we can have tons of information and data from computational material science, and now we are thinking about how to decode some principles among a large amount of materials. So to give one example about the data that we have access to, I am working with the materials project team in University of California, Berkeley. Currently, we have a database of more than 100,000 inorganic materials, while most of them are actually ceramic materials. And they have a variety of properties, including band structures and elastic tensors, piezoelectric tensors, or something like specific materials, for instance, for intercalate secondary batteries. So we have so many materials, and it is sort of like routine that we can consequently predict hundreds of new materials after like a few months of calculations. So here is an example about the work from my colleague. Actually, he calculated all the possible ternary nitride that can be formed from the element in periodic table. So it's made of this kind of a compatibility heat map. It's made up of maybe like 3,000 different compounds for ternary nitride materials. And this is a demonstration about how powerful we can be nowadays to predict materials from high-throughput computation. So what we do here is actually take a prototype formula of the materials and the prototype crystalline structures, and then we're basically doing a combinatorial game. We're combining different compositions and different elements so that we finally end up with calculating everything. So, however, this looks very exciting and promising, right? But for experimentalists, they are always confused. The reason why they're confused is I can give experimentalists 100 new materials that are predicted to have excellent properties. But the first thing they're gonna ask is, how do we make them? It is likely that you can predict 100 materials, but you can synthesize none of them. So this is the next challenge that we want to solve in the pathway of computational material science. So this is actually what I'm going to show you today. So how do we typically make ceramic materials? There are a lot of ways to make ceramic materials, but for most of the case, we are doing solid-state synthesis. And this is a very simple process of synthesis process. What we need to do is actually to collect different powders, which are precursors. They're usually binary oxide, sulfide, or sometimes elemental phases. And what we need to do is actually to mix them, and then we heat it up. So we need to find the adequate temperature as well as a certain gas atmosphere if we want to enhance or prohibit some redox reactions. And if we are lucky, we finally get the materials. But if we are unlucky, which is most of the cases, we're going to end up with impurities. So this is exactly what's going to happen when you do solid-state synthesis of ceramic materials. And if you want to add some science into this process, like the first step is about picking up precursors. When you choose different powders, you're going to end up with a different compound, right? So this is very obvious, right? And the second thing we can play with is the reaction conditions. Like a good solid-state scientist always know the best temperature and the best gas atmosphere for synthesizing certain materials. But if you are a first-year undergraduate student, what you can do is basically try and error. So these are the 2 points that I want to share with you today. Like, how do we use the thermodynamic knowledge and theories to model the selection of precursors as well as the reaction conditions? We call them reaction pathway. All right. So how do we tune the synthetic reaction pathway? The first thing we do is basically tune the precursors. In thermodynamics, this is equivalent to engineer the chemical potential of a certain species. So let me give you a simple example. If you want to make ceramics with material A and B, so you have a variety of choices, right? The most straightforward choices are those binary phases made of A and B that are most stable, right? Those materials are most of the time available in the market. So we have A2B, AB, and AB2, for instance, in this low energy envelope, which is the line colored in blue. So in that case, you have 3 choices, right? A2B, AB, or AB2. It seems that you can randomly pick up some of them and just adjust the stoichiometry to make materials, but actually, when you pick different compounds, you're actually picking different chemical potentials to start with. To give an example, like A actually have a reference chemical potential of A, which is mu0. We put that at 0 for reference. And when you pick 3 different compounds that as shown here, you're actually picking a wide range of chemical potentials from mu1 to mu3. And mu3 apparently have the lowest chemical potential, which stabilizes most of the chemical A. So this is a simple story that may give you some hint about what we should do. We are essentially picking up different compounds in the lowest energy envelope, which we call convex hull, and we're using that to engineer the chemical potential of element A. And we actually have a much more things to do here. We don't only have 3 compounds. We know we have this metal stable polymers, right? So the empty space between A and B, as well as envelope, are the large amount of precursors that we can deal with. Usually we're going to have hundreds or even thousands of them, depending on which composition space you're looking at. So that is actually a very large combinatorial space. So what's going to happen if we choose different precursors and tune different chemical potentials? I would like to describe it as a waterfall principle. It's like a waterfall. We know in waterfall, the gravity controls everything, right? So the water flow from the high point to the low point. So it's actually similar when you are designing a ceramic synthesis. If you imagine the gravity as thermodynamic driving force, then the thermal controls. We have low chemical potential region, right? And we also have high chemical potential region. And in most of the cases, the new materials that you want to make is something in the middle. They're metal stable, but they should be reasonably metal stable. If the energy is too high, you can never make them. So in that case, the reaction pathway becomes very important, because if you come from a low chemical potential, it is very likely you cannot make it, right? Because the thermal does not drive this process. But if you start with a high enough chemical potential, it is likely that the reaction going to happen and stay at some intermediate state. And you can use some experimental treatment to stabilize that metal stable state. For instance, like the usual thing we argue about this metal stable phase, a kinetic stabilization, right? So that is actually the basic idea behind designing the precursors. So let me then give you an example about a real case. So in this Nature Material paper published in 2020 by my colleague Jin Yang, he actually tried to make a sodium metal oxide, which is frequently reported and studied in the field of sodium-ion batteries. So typically, we mix a cobalt oxide with a sodium cobalt oxide, and they're going to end up with a P3 sodium cobalt oxide. This is usually the first phase you see when you do a solid-state synthesis. However, if you play with the precursor a little bit, for instance, if you use sodium peroxide, it's actually going to form something very different. They're going to form actually an O3 phase accompanied by an O3 prime phase. And the reason behind that is you are basically changing the chemical potential of sodium, because like the chemical potential of sodium is larger in the sodium peroxide compared with sodium carbonate. So in that case, you are basically raising up the energy landscape so it can hit some metal stable energy state, which is O3 or O3 prime sodium cobalt oxide. And if you keep annealing these materials for long enough time, they're finally gonna go to P3. And if you're heating up for a very long time, they're finally gonna go to the ground stage, which I'm gonna show you in the next slide. So this is basically a schematic about what exactly happened. So in real experiments, what we do, actually Jin Yang did this in situ synthesis in Theta group. Like we see that when we mix sodium peroxide with cobalt oxide, the first phase is gonna form immediately after 5 minutes, and then you're gonna end up with the O3 phase with a little bit of the leftover precursors. And then if you keep heating it up, the leftover precursors will continue to react with O3 phase, so you end up with O3 prime phase with some other phases left. And if you keep annealing that for until half an hour, you finally end up with a P3, which have even lower energy. So the grand potential basically tells you about the chemical potential, about the energy landscape of the reactions. It's from top to the bottom, but if you stop the heating in the middle of something, it is likely that you're going to stabilize that metal stable phases. So this is what we can do to synthesize a metal stable promising functional materials. So a little bit back to some real computation data, right? So we can also apply this in some other sodium metal oxides, for instance, like sodium manganese oxide. Usually we use manganese oxide mixed with the sodium peroxide. In that case, you're going to form a metal stable O3 prime phase, which is a kind of similar to the sodium cobalt oxide, right? And also, if you mix that with a sodium carbonate, you will never see the O3 prime phase as derived from the in situ XRD experiment. So when we do the calculation for the reaction energy as a function of different precursors, we see that actually we have 3 bars here, like the yellow bar demonstrates what's going to happen if we use sodium carbonate, which corresponding to a lower chemical potential, while the purple bar actually demonstrates sodium peroxide, which is slightly higher chemical potential of sodium. And we can go to the most stable sodium precursor, which is sodium oxide. So in that case, we see that from sodium carbonate to sodium oxide, we are pushing up the chemical potential of sodium, right? As a consequence, we are also pushing up the sodium content in the in the form the sodium metal oxide. So this gives you a flavor that if you are raising up the chemical potential of sodium, it's more likely for sodium to cooperate into this metal oxide framework. So that is actually why you tend to form actually a high sodium content compound. So this is a real example about how do we play with the precursors to tune actually the stoichiometry as well as the structural phases of different materials. So that is pretty much what we can do for precursors. And if we go back and look at the waterfall, right, what else we can do for the waterfall? I'm going to tell you in my next slides, since I tend to like split my slides into less than 20 minutes at least. So I will give you the second half of my stories in the next slides. Thank you again for your attention. I will see you in my next video.